We'll discuss what's on the right part of the board in just a few minutes, give everybody a chance to get into class. We have our third midterm on Wednesday. We're going to do a couple example problems today, which will review some of the chapters 7 and 8 material. And we've done some example problems the last time we met. So we're going to start out with this example. I kind of alluded to it the last time we met, that sometimes you may be asked to find the length of the tube to do a necessary heating of the fluid inside the tube. So this is one of those examples. We start off with the tube of 4 centimeters diameter. The length is unknown, but we're asked to find how long the tube should be for water to be heated from the inlet at 25 to the exit at 75, how long the tube should be. The tube surface temperature is assumed to be constant at 100 degrees C. The water flow rate in the tube is 2 kilograms per second. So in this problem, for properties, to get the Reynolds number, it's not a guessing game because we know T mean in and we know T mean out. So all we do is average those two temperatures. 25 in, 75 out, 50 degrees C, 323 K. Go to the back of the book for properties. Get the Reynolds number, 4m dot pi d mu. Now in the back of the book, under water, you're going to find this. There'll be a mu G and there'll be a mu F column. The G stands for saturated vapor. No, what's in the tube is not a saturated vapor. The F stands for saturated liquid. Yes, that's what we assume water behaves as if it were a saturated liquid. So in the table of water in the back of the book, or in your table of properties for the midterms, for instance, you always use the subscript F properties. There'll be a thermal conductivity, G, Kg, Kf, use Kf. There'll be a Prandtl number, Prandtl G, Prandtl F, use F subscript, saturated liquid. You may or may not need it, but there's a VG and a VF specific. That table, comes, of course, from thermodynamics. That's its history. So you have to go back and say, what was little v in thermo? Specific volume. If you want density, from thermo, density is 1 over little v. So that's how you would get density from the back of the book in the tables, if you need it. Okay, back to here. We get mu F from the tables in the back of the book at the temperature, 323 K. We get the Reynolds number, really big, 116,000, greater than 2,300. It's turbulent flow. Okay, so now we know it's turbulent flow. Chapter 8, of course. Go to the decision tree for the H values that we did last time. There's only one equation for turbulent flow. It doesn't matter whether the tube has constant surface temperature or constant wall heat flux. It doesn't matter if the velocity profiles are developed or not. It doesn't matter if the temperature profiles are developed or not. We said we're only going to use equation 860 if it's turbulent flow. Okay, there it is. If the numbers are, of course, all known now, put them in there and get 6919 for H bar. Okay, so that's step one. Now, you look for an equation that has L in it. Okay, so we try a few equations. Let's try and get Q. Okay, simple equation, Q equal m dot C sub P T mean out minus T mean in. No L on that one. But there's another equation for Q. This one, which is H bar A sub S delta T out minus delta T in divided by natural log delta T out, delta T in. Which is equal to minus T surface minus T mean out. I have to put two things around here. Minus T surface minus T mean in. Natural log delta T out over delta T in. What's going on this diagram? Temperature versus distance, axial distance. Surface temperature of the tube constant at 100. Fluid comes in at 25. Fluid goes out at 75, so there's a picture. What's delta T in? Here. What's delta T out? Here. Okay. These two Q's are the same. Equate the Q's. M dot CP T mean out minus T mean in equal minus T mean, we got T mean out minus T mean in. T mean out minus sine, T mean out minus sine divided by natural log delta T out over delta T in. Oh, and top, of course, our H bar AS. Surface area pi d L. Okay, there he is. There's the L I want. That's the L I want. Solve this guy for L. I know everything. M dot C sub P, T mean out, T mean in. I found H bar. I know everything. Oh, of course, by the way, notice here, T mean out minus T mean in, T mean out minus T mean in, cancel, cancel. Both sides. Do the math, and you get 10.6 meters. Okay. Yeah, question? Yeah.
I think you're missing H bar A as the last part of the Q.
Which one? Oh, up here? Yeah. You're right. Thank you so much. Put in here. Okay, we'll put it right here. H bar AS. Thank you. Good. Got that guy. TS, that's correct. T mean out minus TS. There's a minus sign there. Delta T out is TS minus T mean out. Minus this guy here, TS, that's correct, that's correct. Yeah, we've got that. Oh, okay, he's fine that way. All right, 10.6 meters long, and the water gets heated from 25 to 75. And we used the turbulent flow equation from chapter 8, 860, to find H bar, and then equated the Q's and have the length in the surface area, and then eventually solve for the length. Okay, this guy here, delta T out, is equal to T surface minus T mean out. Delta T I, T surface minus T mean in. Okay, so that guy goes there, that guy goes there. All right, any questions on that then before we go on to the next example? Okay. Now, we've worked a problem involving laminar flow in chapter 8. What did we find? The temperature out and Q. We worked a turbulent flow problem in chapter 8. What did we find? Temperature out and Q. We just worked one here, chapter 8, where we're at to find the length of the tube, oh, and Q. Now, if you want to find Q, just one last thing. If you want to find Q, it's easy. We could have done that the first step. We knew everything. We know M dot, we know CP, we know T mean in, we know T mean out. So you can find Q really simply right away if you want to. It's very simple, it's right here. So two things you could be asked for. Find the length of the tube and find out how much heat transfer has occurred to the water from the tube surface. Okay, now let's, before we work the next problem, let me just quickly say, on the homework, some of the homework problems I gave in chapter 8 contain problem 812. If you see problem 812, ignore it. Don't work it. It's not going to be required. Don't work problem 812. It appears one place in the homework of the syllabus. So just so you know, don't work problem 812. These example problems in the textbook are good to read before Wednesday, midterm. Chapter 6, 2 examples, 6.1, 6.4. Chapter 7, 3 examples, 7.1, 7.2, 7.4. Chapter 8, 4 examples, 8.2, 8.3, 8.5, 8.6. So those are good examples to read before the third midterm on Wednesday. It'll be 2 problems, 50 minutes, just like before. It'll be from chapter 6, 7, 8. Not necessarily one from 7, one from 8. It might be part of one, part of the other. So it might be a mix of them. Bring in one sheet of paper, both sides, equation sheet for you, just like the first 2 midterms. Okay, I think that's it. Any questions on that then? Okay, now we're going to work another example problem. And let me, it's in the textbook and there's the pictures on the board, but I'll just give you, and I'll read the actual problem statement, because it's a little bit complicated. There's one more here. And he gets one here. Okay, 1, 2, 3, 4. I think that's enough for them too. Okay, it comes out of this problem in the 6th edition is 874. In the 8th edition, it's 857. So it depends what edition you've got your hands on. I'll read it. And here's the picture. So I've redrawn the picture from the handout on the board. Water at 290 K and 0.2 kilogram per second flows through a Teflon tube, K value 0.35. So water flows through a tube. The tube wall is Teflon tube. Okay, let me put that down there. Teflon tube, circular, outside radius 10 millimeters, 13 millimeters, inside radius 10 millimeters. Okay, keep reading. A thin electrical heating tape wrapped around the outer surface of the tube delivers a uniform surface heat flux of 2,000 watts per square meter. So heating tape, 2,000 watts per meter. Square meter. Right, okay. Now, he says, while a convection coefficient of 25 is maintained on the outer surface of the tape with ambient air at 300 K. So he gives you H on the outside. No, scratch that out. Nobody gives you H on the outside. You're supposed to find H on the outside. So I'm modifying the problem. I'm saying I don't know H on the outside. The problem he worked in the textbook, he gives you H on the outside, 25. He gives you H 25. No, we're going to find H. But to find H, somebody's got to give us the velocity of the air. Okay, so here's the change. H outside is not given in the problem. But in place of that, the free stream velocity, 1.8 meters per second. Okay. Keep reading. Okay, what do we want to find? Okay, find T of the surface. It says find the surface temperature of the Teflon tube, T surface. Find Q going to the air. Find Q going to the water. Okay. All right, so now on the handout I gave you, there's a resistance diagram. So as I mentioned earlier, way back, early in the class, I said the first thing you want to do with these problems in the homework area of the textbook is try and understand physically what's going on, because there's no use trying to get to the equations of the math unless you understand physically what's going on. What are you given and how do you think you're going to solve for it? You've got to walk your way, talk your way through the problem before the pencil starts moving. Okay, let's see what's going on here. I've got a cylinder, the tube. Here's a Teflon tube. He says, wrap a heating tape around it. Here's the heating tape. Wrap the heating tape around it. Now a Teflon tube here, wrapped around it, a heating tape here. Okay. Now, the heating tape is generating heat. So one way it can get out is go to the air around the outside of the Teflon tube, right. The other way is it can go into the water inside the Teflon tube, right. So now we want to find out how much goes in each one. We go back to chapter 3. There's a resistance of the Teflon tape, of the tube, Teflon tube, a resistance. There's a resistance on the outside to air, convective coefficient. There's a resistance on the inside going to the water, a convective coefficient. There's 3 resistances: air, water, tube. So as he's showing on this, as I did on this picture I got for you, here's what he shows. This is T infinity, the air temperature. This is T of the surface of the tube. This is the temperature of the water in the tube, T mean. This is going back to chapter 3, so it's a good review of chapter 3 stuff. We had a problem similar to this. I worked on the board for chapter 3. Now here comes, of course, the question. What do I do with that heating tape 2000? Well, the first question is, where is it? It's on the surface of the tube. Okay. In our diagram, where's that? Right here, the surface of the tube. What comes in there? Q. They call it Q naught double prime, I think. Yep, Q naught double, or Q double prime. Okay. Q double prime. The heating tape's hot. So some of the heat goes out to the air. Some of the heat goes into the water. This is the resistance convection on the outside. This is the resistance for convection on the inside. This is the resistance of the tube. So once you get that guy drawn, you've got a road map. You've got a road map, and that's critically important to understand the problem before we start using equations to solve the problem. Okay, so we'll start out then, and let's go ahead and calculate energy balance. On the outer surface. All right, what comes in? Q double prime times the area of the outer surface. Q double prime, area of the outer surface. And where does that heat go? Well, some of it goes, well, I'll just put it down. Q air plus Q water. And Q air, TS, he calls this TS outside, so we'll do what he does. TS outside minus T infinity over 1 over H outside, A outside. For water, TS outside minus T mean divided by the resistance of the Teflon tube, natural log R2 over R1, 2 pi KL, plus the resistance convection of water on the inside, 1 over H inside, A inside. Okay. That's chapter 3 stuff now. Chapter 3 stuff. What do I know? Given, I know it. I know it. I know it. Yes. 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 What don't I know? H inside, H outside, and TSO. What am I asked to find? TSO. And we'll put the O means outside. That's okay. Okay, well, you can see what we got to do. This ends chapter 3. Now we jump to chapter 7 and get H outside. Then we jump to chapter 8 and get H inside. So let's start out with this guy. So let's see, we'll do, okay, let's do the inside first. To find H inside. Okay, Reynolds number on the inside. We'll make that Reynolds D inside. 4 m dot pi d mu. Properties at what temperature? The inside temperature of the water, 290 K. Okay, the Reynolds number then, I put the numbers in, 11,790, 11,790. Greater than 2,300, turbulent flow. Over here, water in a tube to find L. Reynolds number, 116,000. Turbulent, what did we do? Equation 860, there it is. So, H is equal to K over D. H inside, 0.023. Reynolds to the 4/5, Reynolds to the 1/3. And that comes out to be 2792. Okay, I've got H inside here, so check that guy off. Got it. To find H outside. Reynolds number. D outside. U infinity. D over nu. Properties of air. At what temperature? 300, back of the book. Yes, sir.
Is the water held at like a constant temperature?
Yeah, good question. Yeah, we're looking at a specific location here in this long tube, here. All you know here is that temperature is 290. Now go down a meter and the temperature will change. We're not looking at that. You'll see no bars over the H's. These are the H values at that particular X location. Okay. So for turbulent flow, how come there's a bar over here, but there's no bar here? Because for turbulent flow, you can, the same H equation with the bar or without a bar. Go to the similar to laminar flow, Nusselt number 3.66, okay? It doesn't specifically say it in the book, but it's the same thing as Nusselt number with a bar over it. Now, is that true for entrance region effects? Oh no, you can't play that game. Not for entrance region effects. The only equation you have for entrance region effects is the bar equation. There is a graph in the book, which I didn't put on the board because you won't need it, but they'll give you a graph for the Nusselt number at a particular x location. Why is that? All right, tell me what the value of Nusselt is at x equal L, 3.66. What's the value at x over L 0.5, 3.66? Here comes the key question. What's the average value of h over that region? Guess what? 3.66. It doesn't matter. Why? Because it's a constant. In turbulent flow, it doesn't matter. Okay, it's a constant. Do you see an x in that equation? No, I don't. It's constant. So this is what the textbook puts there in the textbook. But you can put the bar over it because it's a constant. That's the key. Okay, big long story, but I know what you're saying, and it is a bit confusing. Yes, of course, it is a bit confusing. I understand that. This convection can get real complicated. It can get really complicated. You've got to read it and read it again and 3 times and then think about it a while. Because it looks so simple, but it's not that simple. Believe me, it's not that simple. How about a rough tube? Oh, all bets are off. You better look in the book and see what to do with a rough tube. This is all smooth tube. Okay. All right, here it is. The Reynolds number comes out to be 2945. Now, this is what you don't want to do. You don't want to say, oh, that's turbulent flow. No, that's not turbulent flow. Laminar flow, no. Is there a magic number like 2,300? No. 2,300 is this magic number. Is there a magic number like 5 times 10 to the 5th, 500,000? No, that's flat plate stuff. So what do I say here after I say this? Do I say something like this? No, you don't say anything. Don't say anything. Unless you want to, you can go back to fluid mechanics and say, you know, I'm going to make this up now. At a Reynolds number of 2945, this is how the flow looks. It's laminar all the way around. It breaks off there at the separation point. That's okay for heat transfer. I don't care. Give me the Reynolds number. If you want to do fluid mechanics, here it is. But I don't know. You can find that picture. Go to the fluids book. It's in there for the Reynolds number range. So don't say anything. You can if you want with a picture, but don't say, oh, that's laminar or that's turbulent. No, or it transitions from laminar to turbulent to wake region. No, it's not important. What's important is what's going to come next. What's H bar? Okay, so once you do that, then you say, okay, I'm going to get H bar from chapter outside, chapter 7. What choice do I have? None. We said in class earlier, use the simple equation that's the oldest equation, which is the least accurate equation, which is the Hilbert equation, but it's the simplest one. So use Hilbert equation. There are more recent ones which are more accurate, but for our purposes in class, for homework and exams, we'll get by with the easier one. Why make life too complicated at this level? Use the Hilbert equation, H bar. This is H bar on the outside. This is D outside, just to be specific here. K over D outside. C Reynolds to the M based on D outside. Prandtl to the 1/3. Okay, let's see if we've got that guy right there. Okay, I thought so. This guy right here, sorry about that, but that guy right there, he is our 0.4, not 1/3. Remember the rule. If the fluid's being heated, that N, lowercase n, is 0.4. If the fluid's being cooled, that N, as the exponent, is 0.3. The fluid here is being heated, so that exponent is 0.4. Okay, to find C and M. C and M from table 7.2. C is equal to 0.683. M is equal to 0.466. Okay. Put those guys in there. We know K, we know D, we know Reynolds number, we know Prandtl number, and get H bar out. Get the bar out of there. H outside. We don't want any bars in there. H outside is 25. Now see, that's the value he gave in the problem statement. In the problem statement, he said, assume the convection coefficient's 25 on the outer surface. Okay. I said, no. Nobody gave it to you. You find it. So we found it. But what did we need to find it? A velocity. Did he give a velocity in the problem statement? No. But in the real world, nobody gives you H. You've got to find H. Okay, so now let's put check marks. We just found H outside. There's the equation. What's the unknown? TS outside. So TS outside comes out to be 308.3. What's the area on the outside? The area on the inside. We don't know L. I don't care, it cancels out. There's an L here, there's an L here, there's an L here, there's an L here. They all cancel out. Disappears. So don't worry about that. You don't know L. This is at a particular X location along the tube. Okay. All right, that's degree. Okay, that's K, right. So now we know on our picture here that the temperature right here is 308.3. Hotter than the air, hotter than the water, okay. Now life becomes easier. I want to find Q air. That's Q air. I want to find Q to the water. That's Q water. Q air, Ts outside minus T infinity. We've got all those guys. That comes out to be 207.5 watts per square meter. I divide through by A outside, divide this equation through by A outside. This guy disappears. When I divide through by A outside. Why? Because I want double prime. Why? Because I'm given double prime for Q naught. He didn't call it Q naught, but that's the input power. Everything's in watts per square meter then, based on the outside area. Okay, now here's the dashed lines here. I know it, I know it, I know him, I know him, I know H inside. Divide through by A naught, divide through by A naught, okay. When you do that, you get Q double prime water. $1792.5. So, of course, it checks, obviously. If you want to look at these resistances, you can calculate them now. It's a double prime resistance. You could calculate these resistances. You'd find out that this is like 490, this is on the outside, 0.49. Let's see, yeah, 0.49. The tube resistance is 0.12, and the inside resistance is 0.0057. That's the prime values, if you want to call it that. Okay, because you don't know L, so it's the resistance per length. So where is the least resistance for the heat flow? Oh, into the water, because H, why? Oh, look how big H is, 2792. How about the resistance up here going to the air? 0.49. Water, 0.0057. Why? Well, look at the H over here. 25. Pretty bad. Why? Well, you got air going at a velocity, 1.8 meters per second. And of course, the tube, 0.12. It's between these two guys, the Teflon tube. So you can look at the resistances, chapter 3. So this is a great problem because it involves, it's called combined heat transfer problem. It combines chapter 3, chapter 7, chapter 8. It involves understanding this picture, what's going on from that picture to this picture. Then take this picture and see what you need to find. H inside, H outside. Write the energy balance on the surface of the tube. The heat flux that comes in either goes to the air or the water. Get the H inside, H outside, find this goes to the air, this goes to the water. So it's a great review problem, not just for chapter 6 and 7, but also chapter 3, a resistance diagram of the real world picture. Okay, any questions on that guy then? Okay, if you didn't pick up your old homework from chapter 6, 7. It's up here in front. Chapter 8 homework, again, if you came in late, is due a week from today. A week from today, chapter 8 homework. All right, so we'll see you then on Wednesday.